Hi, this is Ms. McGovern. This is the fifth video in the Electromagnetism series where we're going to look at the force on a current-carrying wire. So let's just think about forces between magnets, something you've done even as a little kid. That if you bring two bar magnets together, there is a force on them. So if you bring a south and a north pole together, so they are opposites, you'll find that they attract each other. And if you bring a south and a south together, or a north and a north together, they are the same pole and they repel each other. Regardless of if they're attracting or repelling, bringing two magnets together induces a force between them. So the same thing happens when you bring a magnet near a current-carrying wire. So we've got a magnet, and then we've got our wire section AB. The wire in the last video we looked at, in video 4, wires have moving electrons. Moving electrons generate a magnetic field, right? So because the wire acts like a magnet and you bring it near this other bar magnet, there's going to be a force between the two. So what we need to be able to do in level 2 is figure out the size of that force and the direction of that force. It's a little bit harder than just two bar magnets together. So the size of the force is given by the formula F equals Bill, where F is the force, B is a new symbol, and that measures magnetic field strength. And magnetic field strength is measured in Tesla. Now, most of the magnetic field strengths you're going to get a very small, 0.00 something. 1 Tesla, for example, is an incredibly strong magnetic field. I is current, which we've come across before, measured in amps, and L is the length of the wire in the field. Now, the direction, we're going to use the left-hand rule, the same rule we've been using all the way along, and I'll show you how to use it now. So, when we're dealing with the direction, first of all, we use that left-hand rule to find the field around the wire. And then what we're doing is we're looking for where the external field, this is like, for example, the bar magnet, and the wire's field are opposite each other. Because we know that opposites attract, then the force on the wire is directed towards that spot we just found. Now, it sounds a little bit complicated, so let's just do a couple of examples to work that through. So here I have an external field. Let's pretend I've got, say, a horseshoe magnet to make this, and this field line, these field lines are coming out towards me, out of the page towards my eyes. I then bring a wire. Now that would be connected to a full circuit, but I'm just taking a picture of just the wire so I can just deal with one thing at a time. The current's going down the page. So the first thing I do is use the left-hand rule to find the field around the wire. Now my thumb points upwards because that's the way the electrons go. So when my thumb points upwards, I've got my fingers curl around the wire. I have on the right-hand side of my wire, my fingers are coming up towards me, and then they keep curling around and they go into the page on the left-hand side of the wire. So that's why I have the crosses in the green there. So now I'm looking for where the external field, the white one, and the wire's field, the green one, are opposite each other. So it's on this left-hand side because I've got white dots everywhere, and the opposite of a dot is a cross. And opposites attract. So that's towards the left of the wire. The whole wire gets forced towards the left. So one of the things that might seem intuitive from that picture, regardless, you've got to remember, is that the wire, the magnetic field, and the force are all perpendicular to each other. So if they're not perpendicular, if the wire was going, or if the current was going in the same direction in this magnetic field, that would not make a force on that wire. So here's another one. We have a magnetic field lines going up the page here, and let's say I've got a wire moving to the left. Now first of all, are those 90 degrees to each other or perpendicular? They are, so that's going to generate a force. So let's figure out the direction of this force. So the current is moving to the left, which means my electrons are moving to the right. So I get my left hand, I point it to the right, and the way I grab there means that above the wire, I've got my fingers going into the page, that's crosses. Below the wire, I've got my fingers coming out of the pages, that's dots. And remember, it's circular. Now I'm looking for opposites, but at the moment I've got crosses and dots, and I've got arrows that go up. I'm not really sure what the opposites are here. So this is not very obvious which way the force is. So I actually need to think about the field lines all the way circular around this wire. I've got to think about the full circles. And I'm going to get my answer by just thinking about what's the field lines doing in front of the wire, like up towards me and above the screen, and below the wire, so behind the screen. So with my fingers, you can see there, my fingers with this diagram here, and imagine I was gripping the wire through here. My fingers are in front of the wire pointing upwards. So I can draw that as an up arrow like that. And then if I was to manage to keep curling my hands around while pretending I was holding that wire, my fingers would be pointing down behind the wire. And the way I show that is with a broken arrow like this. So now I've got these arrows show the full field going around the circle. Now I can make a comparison with the external field. That's the white one. And I'm looking for opposites. So what's opposite these up arrows? It's this down broken arrow here. So those are opposites. What direction is that? That's behind the wire, into the page. And so the force on this wire is into the page. That is a tougher question, sort of the toughest you'll get, because you have to really think about all the field in front of and behind of as well to get that one right.